So the title is Krein-Milman's theorem for homogeneous polynomials. And what are we going to talk about today? First of all, the plan is the following. First of all, I will try to give very fast the classical definitions of extreme points and formulate classical Krein-Milman's theorem. The second part is Krein-Milman type theorem for linear operators. And after that, I'll present the main result of this talk. This is Krein-Milman's type theorem for homogeneous polynomials. So let me start with the definitions. So let X be a real vector space and non-empty subset C of this set is said to be convex whenever for 2 points of this set, there is an interval which entirely is included in C. The straight definition is on the slide. A convex whole, which is denoted by co-A of X, of A, is the smallest with respect to inclusion convex set that includes A. And it is easily to prove the fact that the convex whole of set A can be counted as follows. It is the set of linear combination, convex combinations of elements from A. One more definition, this is extreme point. Extreme point of convex set A, I give it for convex set, is a point U. And it is defined as following. The point U is an extreme point if there is no such an interval with ends xy in A, which contains U, there is no such interval. And it is the set of all extreme points is denoted by XA. We'll need this notation. So simple examples. For example, in R2 space, two-dimensional LP space, LP is the set of all sequences which are P-summable. We consider, in this example, we consider three kinds of norms. When P is equal to 1, we have rhombus. The unit ball has a form of rhombus. When P is equal to 2, the unit ball is a circle. And one more case, when P is equal to infinity, we have a square. So here we can see where the extreme points are situated. These are the corners of rhombus and circle, and all the boundary of the circle, and corners of rhombus and square. So in classical Banach spaces, also I will list.
Just am I right that in all these examples the sets are convex?
Yes, yes. We give the, of course, we can give the definition of extreme point not for a convex set, but it is a little bit strange and is not in use. That's why we give the definition for exactly convex set. So in classical, in some Banach spaces, I list here the the sets of extreme points, and from this slide one can see that there are different cases. For example, there are cases when the Banach space do not have extreme points, it's empty. For example, C0, these are the space of sequence which are convergent to 0. There are spaces where are extremely many extreme points in the set of extreme points, and there are also sets where are countably many, and I don't know, also for example, the case when the extreme space is entire sphere. So there are many cases, and in all these cases which are listed here, one can see that the set of extreme points is less than the unit ball itself. And so the question is how to reconstruct the space, the unit ball by means of extreme points. And the answer was given in 1911 by Minkowski, and this theorem says that if C is a convex compact set in a it was given in finite dimensional, of course, case. So it says that if C is convex and compact subset of a finite dimensional space, then C can coincide with the convex whole of all of the set of all extreme points of C. And essential specification of this case, of this theorem, was given by Kara-Teodori also in 1911. It was about the following. If this set A is a subset of finite dimensional, namely m-dimensional space, then one can count the convex hull of this set by means only of m+1 points in this m+1 extreme points. So using the if we denote A to be the set of extreme points of C, and using Minkowski and Kara-Teodori theorem, one can get this representation. This means that convex compact set, subset of a finite dimensional m-dimensional space, had the following representation. It is the set of m+1 convex combinations of extreme points of C. So Kara-Teodori's theorem in 2 dimensions states that for any point X in the convex hull P, we can construct a triangle with vertices in P, and that which encloses X. So, but in infinite dimensional case, Minkowski theorem doesn't work, and it may happen that the convex hull of extreme points of unit ball is a proper subset, which means is strictly less than a unit ball itself. And to show this, let us consider one more example. We consider L1 space. These are the this is the space of all sequences which are summable, absolutely summable, and we see that the unit ball of this space consists of all sequences with which are absolutely summable, and which absolutely sum is less or equal to 1. Its extreme ball consists of all sequences. I denote them plus minus en bold, which means that in the nth place, there are plus minus 1. And the convex hull of this of its extreme points looks as follows. It means that it is essentially the sequences which are eventually equal to 0. And from this example, one can see that the convex hull of set of extreme points of unit ball doesn't coincide with the unit ball itself. And in 1940, a fundamental result was established by Crane and Millman. It says that if that a convex and compact set coincides with the closure of the convex hull of extreme points of this set. So these are the notations. And a very, very important corollary from this theorem, from the Crane-Millman's theorem, says that for a given norm space X, the dual ball coincides with the, I will say, weakly closed convex hull of its extreme points. What is this about? Why it is important? It is important because here we step to linear functions. Of course, here we work with functionals in this corollary, but this is a step to linear functions. And the question is, what if we substitute the real space by a Banach space Banach space Y? And the interest to this question started from the works of Phelps and his co-authors of 1960s. Here are listed only some of them. I don't think that it is the full list, but only some of them which were done in this, what was done in this direction. Next, I will, I think it will be very useful to announce here the typical result which was obtained in numerous works listed here and not listed. But first I will give two definitions. They are very similar with those ones which I gave before, but it is necessary to announce them. Okay, we work in a Banach space, and CK is the space of all continuous real functions on the compact Hausdorff space K. And by the symbol LXCK, we denote this space of linear bounded operators from acting from X to CK. And now here we introduce operator convex, or also we will denote it lambda convex subset, and the definition is almost the same that I gave before. The convex combination lambda 1 T1 plus lambda 2 plus, T2 is in omega for all T1 T2 in omega, and lambda 1 lambda 2 in lambda plus, which means they are positive and they are functions, because we denoted lambda like CK, and the sum of lambda 1 lambda 2 is the operator is a unit on K in Hausdorff compact space K. And also one more definition: the smallest by inclusion operator convex set in LXCK containing A is called operator convex whole, just the same as in as I defined it previously, and is denoted by this symbol co lambda A. And one of the typical results which were obtained in this direction is the following. If K is a totally disconnected, then unit ball of the space L is the pointwise closure of the operator convex holes of its extreme points. But Crane-Millman's theorem does not immediately yield these and similar results which were obtained. The reason is the fact that the closed convex sets of operators and compact are compact only in very special cases. So the problem was in compactness. During next 30 years, a number of authors worked in two directions about this problem. First was to give an explicit description of extreme points of different convex sets of linear operators, and the second direction was to obtain different Crane-Millman's types theorems to try to generalize it. And here I again list several papers, but the main general results was obtained in the last two papers. And here the result was obtained for the vector lattices. And here, of course, I have to stop and give a small, slight definition of a vector lattice. A real vector space equipped with an ordering which satisfies two axioms. First of them is that the equalities can be added. The second is that the equalities can be multiplied by positives. So such a pair is a vector lattice if and only if, just a moment. Oh, yeah. If and only if for any two elements from X there exists supremum and infimum. Also, we'll need the definition of order interval. You can see it on the slide. It is a set of a form AB, and the vector lattice E is said to be Dedekind complete. It is in European literature. In Russian literature, it is Kantorovich space, K space. So we call by this term the vector lattice if for any order bounded space there exists supremum and infimum. All classical Banach lattices are the examples of Banach. All classical Banach spaces are example of vector lattices with ordering, which is introduced if we speak about the space of functions, it is introduced pointwise. If we speak about the space of sequences, it is introduced coordinate wise. And also for for the further talk, I would suggest you to keep in mind every time when I call say vector lattice, I suggest you to keep in mind the space of measurable almost everywhere finite real valued functions. It is just for convenience for understanding the subject, and it will not destroy anything in the logics of the talk, but it will be very then it will be easier to understand what about I'm talking about. We'll need 3 more definitions. First of all, let me denote by F italic XF the space of all mappings acting from X to F, and we say that a subset omega is weakly order bounded if omega from X is equal to all values of T on X, and this space is order bounded in F for all X. Also, we call omega pointwise or closed if for any sequence Ti in omega and every mapping T we have T in omega provided that Ti X is almost everywhere convergent to Tx for all X. And also operator convex notion, it was already given. I just want to emphasize that by alpha beta I denote the orthomorphisms, positive orthomorphisms, and let us think that it's a multiplicators. So here is a formulation of Kusraeva-Kutateladze theorem, which was obtained in 1982. This is a Crane-Millman's theorem for linear. Crane-Millman's type theorem for linear operators, and it says that a weakly order bounded and operator convex set omega of linear operators acting from a vector space X to a Dedekind complete vector lattice F is the pointwise order closure of the lambda convex operator convex hull of the set of extreme points of omega. Here the paper is presented, cited, and what I want to say here what was obtained essentially. Essentially, the following was done. They got rid of the compactness. They substituted compactness of the set by weakly order boundedness, and this was essential. But also I want to emphasize once more that the resulting space for linear operators is a vector lattice, and also I want to say, as far as I know, there is no result when the resulting space is not a vector lattice, because the vector order structure is essential here. And now the main result, it is Crane-Millman's theorem for homogeneous polynomials. Also, I have to first I have to define the notion of homogeneous polynomial. So let us consider 2 vector spaces. They can be vector lattices, but for the general definition, they are vector spaces E and F, and a mapping between these 2 spaces is said to be S homogeneous polynomial, a polynomial of degree S, if for some multilinear operator phi acting from Cartesian product of E to F, we have the following. P is representable as a composition of this multilinear operator with a diagonal operator, and here you see the last equality. This is the polynomial defined. Here phi is called generating, and also for every homogeneous polynomial there exists only one symmetric unique symmetric phi, which is called associated. This is just about the theory of homogeneous polynomials. And also we'll need the notations by O big times x and theta n. It's bad. You can see it, I hope. Respectively, we call n multiple algebraic symmetric tensor product of a vector lattice X and an n homogeneous polynomial which acts as follows. By these two symbols, we denote the space of homogeneous polynomials and the space of linear operators. And the next lemma is called linearization of polynomials. It is very useful lemma which shows us the connection between these two spaces. And this connection is made by means of the mapping. You can see it on the slide, and it is a linear isomorphism between these two spaces. This linear isomorphism, this linearization result gives us an opportunity to transfer all well-known theorems, properties for the space of linear operators to the space of polynomials. And it is done by means of the following theorem. Here we consider two spaces, the space of homogeneous polynomials, omega, which is called, and we will note it, omega, and omega with index L, the space of linear operators, which are corresponded to each other by linearization. Such properties of omega, like weakly order boundedness, operator convexness, and pointwise order closedness are also true for the omega with index L. And these theorems opens the way for, as I said, extending results on the extremal structure of convex sets of linear operators to homogeneous polynomials. And here on this slide, the main result is presented. What it says that if X is an arbitrary vector space and F is Dedekind complete vector lattice, then omega this is the weakly order bounded operator convex is weakly order bounded operator convex and pointwise order closed set, then the following representation holds. What we can see here, we see that omega is represented as a order closure of a convex whole by CL we denote closure. We denoted it like bar previously. So order closure of a convex whole operator whole. Oh, thank you. Convex operator whole of the set of extreme points of omega. So this is the type, the Crane-Millman type theorem for polynomials. And also, it was interesting to see what will happen if we change the resulting space by Banach lattice, and then we get the following corollary. F is Dedekind complete Banach lattice, almost the same. I will not stop on details here, but the change is the following, that here we get pointwise normed closed set. It will be pointwise normed set. Here it was operator convex and pointwise order closed. And also we'll need one more operation. I will not stop on it, but it is necessary. It is mixing. And so we have the analogous of Crane-Millman theorem for homogeneous polynomials. I think I'm done. Thank you for attention.